let's analyze in some more detail what's going to happen with the argument of our tau complex variable when we cross this forbidden region of the defined by the position of the branch guide. Well, initially, our tau are defined by the following values of the argument. Well, suppose this angle here at the origin is alpha, and the argument of tau initially belongs to the region from pi minus alpha. Oh, sorry, this is a pi minus alpha angle, but since we move in this clockwise direction, it's minus pi plus alpha. And on the top, it reaches the value of pi plus alpha. However, after the deformation of our contour, here, as you see, the upper part of the contour leaves the origin in pi direction. But the lower part, here it is, I drew it with a dashed line because it belongs to the lower Riemann sheet. So the lower part arrives at the origin in minus pi direction because this is minus pi plus alpha, and it just rotates a little bit more into this minus alpha direction. So it's minus pi plus alpha minus alpha. So it arrives here at minus pi direction. That's it. That's the only difference. Otherwise, it's just very simple. And how do we perform the estimate? Well, we just realizing that the crucial contribution comes from the origin in T complex plane. We expand our h of tau function, which is multi-valued, in the vicinity of the origin. The expansion in its most general form looks as follows. So it's almost Taylor-like expansion, but the powers, not just n, but n plus some real, not necessarily, but some plus some number s, where s may be real or even complex power. So that's the Taylor expansion in the most general form. Now we plug it in into our initial integral and just perform the integration, because the integration becomes elementary due to the simplicity of the exponent here and pre-exponential factor, which is tau to n plus s. So here we go. The integral is split, decomposed into the sum of very simple integrals. And each of these integrals is just the integral along the Hankel contour. And as you remember, it's a gamma function up to 2 pi I term. Well, naturally, there is additional lambda factor here, so it becomes a gamma function after the rescaling lambda tau equals to e, for example. Once you perform this rescaling, what you eventually arrive at is 2 pi I divided by the gamma function of minus n minus s, and divided by lambda to n plus s plus 1. And naturally, there is a prefactor. Sorry, I actually dropped it here. So the prefactor is e to lambda f of x naught. Here it is, and here, of course, it is. And here it is in front of our sum. So here is how the general asymptotic estimate is made. And the procedure is quite general, and you can use it with any type of the integral. Well, sometimes in the textbooks, this gamma function in the denominator is substituted with gamma function in numerator with the help of so-called mirror identity. And indeed, gamma function of n plus s plus 1 is simply pi divided by gamma function of minus n minus s multiplied by sine of pi n plus s with negative sign here. So we can substitute it and arrive at the just more canonical expression with gamma function in the numerator. And this series, by the way, is usually an asymptotic series. And sometimes the whole asymptotic method, which was just discussed, is called the Watson lemma in asymptotic analysis. Right, so then just one of the ways to perform that kind of estimates when our f of x function doesn't have saddles in the complex plane, or for some reason these saddles are unreachable in our problem. There is another treatment which is almost identical to this one, and let me show it to you in just 2 minutes. And another quite analogous way to look at the deformation of the contour, but without the slipping on the lower Riemann sheet of the Riemann surface of the multivalued function, looks as follows. So again, we have the initial position of the branch cut. Here it's just inclined slightly below. But what you can actually do is to deform the branch cut in such a way that it obeys the position of the steepest descent of the contour. So for example, for this picture, that would mean since our steepest descent direction is pi, negative real axis of tau, then what we do, we deform the branch cut itself. Of course, as you understand, the crucial tau for this integral are the vicinity of the origin. So actually, you need to deform the branch cut direction just in the vicinity of the origin, and then it can continue in the same way as it was before. But once you've done this, you don't have to include another Riemann sheet in your consideration. And sometimes it just helps you avoid unnecessary complexity of your problem. Because now your contour belongs entirely to the upper Riemann sheet. And of course, the rest of the consideration is just completely identical to what we just discussed before, and you arrive at the same answer, just word by word, you reproduce the same kind of expression. So that's it. Use it at your convenience. Sometimes just it's more natural to slip on the other Riemann sheet of your Riemann surface to build the asymptotic estimate. But sometimes you just bend the branch cut and arrive at the same identical expression. But of course, in the latter case, you need to change the allowed regions of your argument. Sometimes because in most cases they are fixed initially by some physical condition of your problem. Here you just change them slightly, but it's just completely equivalent way to look at the same problem.